Next, let's take a look at a few examples of applying the formal definitions of the limits that we reviewed in the last video lecture. So first of all, recall that the limit as x goes to infinity of f of x is equal to L means that for every epsilon greater than 0, there exists a number t such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x, or actually whenever x is greater than t. So in other words, recall that this means that the outputs of f of x are within a tube of width epsilon centered about the horizontal line y is equal to L whenever x is large enough. So there's always some point of no return for any size epsilon tube such that your outputs will be trapped within that tube for all x larger than that point of no return. So let's see an example of this. So let's prove that the limit as x goes to infinity of 1 over x squared is equal to 0. So prove that this limit equals 0. This makes sense because the denominator is going to infinity, whereas the numerator is fixed. So when you're dividing by larger and larger numbers, the output is a smaller and smaller and smaller number, so therefore the outputs go to 0. In fact, we know exactly kind of what this looks like, something like that. That's kind of a rough sketch of 1 over x squared. So to prove this, we have to show that for any size epsilon, the difference between the output, which is 1 over x squared, and 0 will always be less than epsilon as long as x is large enough. So for a given fixed epsilon, which is arbitrary, we don't set it as, we just assume it to be known, like whatever somebody comes and tells me is the value of epsilon, I should be able to return a value t. I should tell you how long you have to wait until you're within that epsilon tube. So to start the proof, we say let epsilon greater than 0 be arbitrary. So basically whatever follows will be valid for any size epsilon greater than 0. And so basically we want to show, so we need to find the number t, a number t such that the absolute value of f of x, which is 1 over x squared, minus L, in this case is 0, will be less than epsilon whenever x is greater than t. So so for a fixed epsilon, how large do we have to make t for this statement to be true? Well, if we look at this, the one on the left is the same as just 1 over x squared is less than epsilon. And that's the same as x squared is greater than 1 over epsilon. So recall that when you take the reciprocal of a fraction, when you have an inequality, so when you take the reciprocal of both sides, it flips the direction of the inequality. So 1 over x squared less than epsilon is equivalent to x squared is greater than 1 over epsilon. And you can always try it with a sample number to see that it works. And then we take the square root of both sides. So we get x is greater than 1 over the square root of epsilon. So 1 over x squared less than epsilon is the same as saying x greater than 1 over root epsilon. So it's pretty clear in this case we should set t to equal 1 over the square root of epsilon. So as long as t is equal to 1 over the square root of epsilon, it will be true that 1 over x squared will be less than epsilon. So when writing up the actual proof of this, now that we know what the value of t is, the proof itself, let me just kind of erase this. So the proof itself would be written like this. Let epsilon greater than 0 be arbitrary and let t equals 1 over the square root of epsilon. So then x greater than t implies that x is greater than 1 over the square root of epsilon, which implies that x squared is greater than 1 over epsilon, which implies that 1 over x squared is less than epsilon, which implies that the absolute value of 1 over x squared minus 0 is less than epsilon. So we see that x greater than t implies that the absolute value of f of x minus 0 is less than epsilon, and then that proves the result. Right? So we've showed that this definition of the limit as x goes to infinity is satisfied. So for our next example, we'll take a look at a limit as x approaches a constant, and this one's going to be a little bit trickier. So here we'll take the limit, well actually let's just review the definition. So the limit as x approaches c of f of x is equal to L means that for every epsilon greater than 0, there exists a number delta greater than 0 such that the absolute value of f of x minus L less than epsilon whenever 0 is less than x minus c is less than delta. So in other words, for any epsilon tube where you make a horizontal epsilon tube about the line y is equal to L, make it as small as you want, but regardless of how small you make it, there will always be there's always a deleted neighborhood close enough to x is equal to c such that all of the outputs will end up in that epsilon tube. So no matter how close you look, in terms of the vertical outputs, there's always a small enough neighborhood around x is equal to c such that the outputs will lie that close to the output y is equal to L. So let's use the definition to prove that the limit as x approaches 3 of x squared is equal to 9. Which makes sense intuitively because we know what the graph of y is equal to x squared looks like. We know that when you evaluate x squared at x is equal to 3, you get 9, and we know that there are no holes or jumps or anything like that. But we want to prove this using the rigorous definition of the limit. So in other words, we want to prove that for any epsilon greater than 0, we can always find a neighborhood small enough such that if x is closer to the number 3 than delta, then x squared will be closer than the number epsilon to 9. So in other words, x squared and 9 will be no further than epsilon apart as long as x is close enough to 3. So again, we start off by saying let epsilon greater than 0 be arbitrary. Now the trick is to find delta. Right? So the problem is, how do you find delta? And delta will depend on epsilon, because regardless of what epsilon somebody gives me, I can say, okay, use this delta, and then I'm guaranteed to get the condition that I have up here. So to see this, let's just take a look at what we have. So f of x is x squared, and then minus L, in this case L is equal to 9. So x squared minus 9 less than epsilon whenever 0 less than x minus 3 less than delta. So the whole trick here is to find delta in terms of epsilon. So how close does x have to be to 3 in order for the outputs to be closer to 9 than this arbitrary epsilon? And then that closeness, of course, depends on epsilon, because the smaller you say epsilon is, maybe the closer you have to be to 3 for x to be to 3. Now the condition that the absolute value of x minus 3 less than delta can be visualized if you look at the x-axis. So here's the x-axis, here's x is equal to 3, and here's 3 minus delta and 3 plus delta. So saying that x minus 3 in absolute value is less than delta is equivalent to saying that 3 minus delta is less than x, which is less than 3 plus delta. In other words, it's equivalent to saying that you're somewhere in this open interval. And the reason is if you think of an arbitrary x position, say it's right here, this distance is simply the absolute value of x minus 3. So the absolute value of x minus 3 tells you the distance between the point x and the value, or the point x is equal to 3. So by saying that the absolute value of x minus 3 is less than delta, is saying that x is no further away from the point 3 than delta. So what we can do is kind of approximate this x plus 3 factor away, right? So we can restrict delta to be no larger than 1. So we can say delta has to be less than or equal to 1. So that means that this interval, whatever it is, will be between 2 and 4. And I can do that because I can add conditions on delta. So I'll take them into account separately at the end. So I'll have one condition that depends on epsilon, but if that delta that depends on epsilon gives me a number larger than 1, I'll just chop it back down to 1. I can always choose a smaller interval, right? Because the definition for the limit just says that there exists some small x interval such that this works, right? So if I have one size one, I can always make it smaller. So I'll let delta be less than or equal to 1, which means that x plus 3 will be x then less than 4. So x plus 3 has to be less than 4. Because if delta is less than or equal to 1, this interval is between 2 and 4, so x plus 3 will be between 5. Oh, I guess I take that back. X plus 3 will be less than 7. X is less than 4. X plus 3 has to be less than 7, which is fine. So what we have is as long as delta is less than or equal to 1, so as long as delta is not larger than 1, we have the following. The absolute value of x plus 3 times x minus 3 will be less than, well, x plus 3 less than or equal to, x plus 3 is less than 7 in absolute value. So it's just less than 7 times x minus 3. And we can set this less than epsilon. So basically what we can do here is say that, well, this is true whenever x minus 3 is less than epsilon over 7. But of course, x minus 3 has to also be less than 1. So for our delta can just basically be the smallest, either 1 or epsilon over 7. Right, so that guarantees that this delta is not larger than 1, but also it's definitely as small as you need it to be. So basically the proof of this would then look like the following. So we already said this, I'll write it out again. So the formal proof when we write it out would say that be written as follows. So let epsilon greater than 0 be arbitrary. So that's the arbitrary epsilon. And then given that epsilon greater than 0, you can even say given an arbitrary epsilon greater than 0, we define, so let me use define instead of let. So then define delta as the minimum of 1 or epsilon over 7, right? So since delta has to be less than or equal to 1, right? There's no way delta can be greater than 1. X plus 3 has to be Okay, so x plus 3, that's where the 4 comes in. So we want to consider x minus 3 less than delta implies, so it implies a few things. It implies that, well, delta is less than or equal to 1. So this implies that x has to be less than or equal, probably less than 4, right? So since delta is less than or equal to 1, and x minus 3, the condition that x minus 3 is less than delta implies that x has to be less than or equal to 4, right? Which implies that x plus 3 has to be less than 7, or less than or equal to if you want. So x plus 3 has to be less than or equal to 7. Okay, so since delta is less than or equal to 1, the condition that x minus 3 in absolute value is less than delta, therefore implies that x is less than or equal to 4, which implies that x plus 3 is less than or equal to 7. So thus, the absolute value of x squared minus 9, which is equal to the absolute value of x plus 3 times x minus 3, is going to be equal to less than or equal to 7 times the absolute value of x minus 3. So this is whenever x minus 3 is less than delta. But then since x minus 3 is less than delta, delta is also less than or equal to epsilon over 7. And then this is true whenever x minus 3 is less than delta. So actually, this is going to be less than. Right, so basically whenever x minus 3 is less than delta, x squared minus 9 will be less than epsilon. The reason, well, 1, since delta is less than or equal to 1, x plus 3 will have to be less than or equal to 7. Second, since delta is less than or equal to epsilon over 7, x minus 3 will also be less than or equal to epsilon over 7. So actually it will be less than epsilon over 7 because x minus 3 is less than delta, and delta is less than or equal to epsilon over 7, so that's where you get this connection right here. So that proves that the limit as x approaches 3 of x squared is equal to 9. So you can see how sometimes, you know, these can be a little bit tricky and confusing at first, and they take a little bit of creativity and specialization. Like this isn't necessarily a standard trick that will work on all of them to do this with x plus 3, but you just have to get on the ground, look at it, think about it, and see what's going on and do the best you can. And, you know, sometimes these problems can take a while to figure out, but just, you know, the best thing to do is get creative with them and, you know, stick true to the original definition. Basically, you're just executing this initial definition. So basically, think of epsilon as something given, and you just say, well, how small do I have to make delta to get this to work? In other words, to get this condition implies that condition. And that's basically what you have to do.